And it's a great pleasure to introduce Anna. Anna is a professor at Princeton. She's got many interesting, nice work in minimal services attached to eigenvalue, now free boundaries. So, very looking forward to her talk. Please.
Thank you, Gabriela. Thank you for the introduction. And let me thank also all the organizers for the invitation. It's such a great pleasure to be here. Thank you so much. So today I'm going to talk about this joint work with Wanderson Lima from Universidade Federal do Rio Grande do Sul in Brazil, which gives a connection between eigenvalue problems. Professor Antonio, there's a seat over here, please. You're my, it's an honor to have you here. Okay, so this work gives a connection between eigenvalue problems and free boundary minimal surfaces in spherical caps. So I'm going to start by recalling the definition of a free boundary minimal surface. Okay, so here your ambient space is a compact Riemannian manifold with boundary. And we have sigma, a compact surface that is properly immersed in your ambient space. So that means that when you look at the intersection of your surface with the boundary of the ambient space, you only see boundary points, okay? So we say that sigma is a free boundary minimal surface in your ambient space if it's minimal in the usual sense, so mean curvature vanishes, and second, when the surface will meet the boundary of the ambient space in a 90-degree angle. So the conormal along the boundary of your surface is orthogonal to the boundary of the ambient space, okay? For the Euclidean three-ball, we have these two classical examples. You have here the equatorial disk. You take any plane passing through the origin, you intersect the ball, you get a free boundary minimal disk. And on the right, you have here the critical cat line. And this beautiful picture here was done by Mario Schutz. He has a website, and he kindly let us use it. He has a website where he has lots of pictures of free boundary minimal surface. There, play with them. So you should check it out. Okay, so you can also look at these surfaces in a more variational point of view. So you can look at them as critical points for the area functional with free boundary condition. So in this context here, you look at your surface, a compact surface with boundary, and you consider a one parameter family of variation on immersions. So here we are denoted by phi t, the one parameter immersions, and we are denoted by x, the variational vector field. So this condition of letting your surface vary freely along the boundary of your ambient space tells you that when you look at this variational vector field along the boundary of your surface, it is tangent to the boundary of the ambient space. Okay, so when you look at the first variational formula for the area, and here it's a little bit different from the case that Dan Pedover mentioned last time, because here we are letting the boundary vary, you get this formula. Okay, so you see that your surface will be a critical point for the area functional with this condition, if and only if this is 0 for any x with this condition that you take. So this tells us that your surface is a critical point for the area functional with the free boundary condition, if and only if the mean curvature vanishes and the conormal is orthogonal to the boundary of your ambient space. So it's exactly the definition, the geometric definition that we have. Okay, but in this talk, we are interested in the connection between eigenvalue problems and minimal surfaces. And one example of such connection is the relationship between closed minimal surfaces in spheres and Laplacian eigenvalue problems. So here in this context, we have a closed Riemannian surface, so compact without boundary. Given the metric G, you can define the Laplacian. And we know that a value is an eigenvalue for the Laplacian if you have a non-trivial solution for this equation. And as Dan also mentioned yesterday, we know that this operator has a discrete spectrum that goes to infinity. And also the first eigenvalue for any metric that you have is always 0. So when we talk about the first eigenvalue, we always mean the non-trivial one, which is lambda 1. Okay, and in the 60s, Takahashi, he observed the connection between minimal surfaces in a sphere and eigenfunctions of the Laplacian. And he proved that if you have an isometric immersion of your Riemannian surface here into a sphere, this immersion will be minimal if and only if the coordinate functions are eigenfunctions of the Laplacian with eigenvalue 2. Okay? So, but now let's forget a bit for the immersion and let's concentrate on the following eigenvalue problem. So given any closed surface on M, you can consider this functional. Here you give me a metric G, I look at the first non-trivial Laplacian eigenvalue and multiply by the area with respect to this metric, and I can take the sum among all possible metrics on that surface. We call this lambda 1 star. So the first question that you ask is whether this quantity is finite. And here, to have a meaningful question, you need to put the area here, otherwise you always get infinite numbers. So to have a meaningful question, you put that so you have a possibility of this being finite, and it's actually always finite. It was proved first by Hirsch. He was the first one to consider this quantity here, and he concentrated on the case of the sphere. Then Yang and Yao, they proved for any orientable surface, and then Karpukhin, he observed that is also true for the non-orientable ones. Okay? And once you have that this quantity is finite, the first natural question that you can have is whether you do have a maximizing metric for that. And if the answer is yes, you can ask, what do you know about it? Is it explicit? Do you know it? What properties does it have? So in that direction, Nadarashvili, he proved that if we do have a maximizing metric, then your surface endowed with this metric can be immersed in some sphere as a minimal surface by first eigenfunctions. Okay? And for the existence case, I'll have Petridis, who's there in the back, and he's going to give a talk later. So Petridis worked on this, and he proved the existence of a maximizer when you concentrate on a conformal class, but that will only give you our harmonic map. Okay. And he also proved this nice result here, where if you denote by n gamma, the closed surface with genus gamma, he proved that if you do have this kind of gap inequality, this jump inequality if you want, then you can show that the maximizing metric for n gamma plus 1 does exist. Okay, so if you want to prove the existence of a maximizing metric, you just need to check this inequality here, which turns out to be very, very hard to prove. But it's awesome because now we have a paper by Karpukhin, Kuzmin, McGrath, and Stern, where they were able to prove a kind of a weaker inequality to that, but using Petridis' result, they were able to conclude that for any genus gamma, either the maximizing for n gamma or n gamma plus 1 exists. Okay, so we are almost there, still something to be done. Okay, now that's what we have so far for the existence. Now we can ask about the ones that we know that we have them explicitly. And for that, well, the case of the two-sphere, Hirsch proved that we do have the round metric as the maximizing one. The projective plane was done by Li and Yao. It's also the round metric. For the case of the torus, from the work of Nadarashvili, Gihua, Karpukhin, and Medvedev, you conclude that the flat equilateral metric is the maximizing one. The case of the Klein bottle was done by El Sufi, Giacomini, Jazar, and also Jacobson, Nadarashvili, and Boterovich. And we also have that for orientable surface of genus. Good. We also have another example of a connection between eigenvalue problems and minimal surfaces, and this one is the connection between free boundary minimal surfaces in Euclidean balls and Steklov eigenvalue problems. So here in this context, your surface is a compact Riemannian surface with boundary. We are going to denote by nu the outward conormal to the boundary. And we have for any metric G that you have here, you have the Dirichlet to Neumann map that takes a function that is defined on the boundary of your surface and gives you back the normal derivative of its unique harmonic extension. Okay, so you have an eigenvalue for this guy if the normal derivative of the harmonic extension is a multiple of the function that you started with. Okay, so this operator is also self-adjoint, has discrete spectrum that also converges to infinity, and also has the property that for any metric that you take, sigma naught is always 0. Okay? And they're called Steklov eigenvalues. Okay? And Fraise and Shane, they observed the connection between free boundary minimal surfaces in the ball and Steklov eigenfunctions. They proved that if you have an isometric immersion here that is proper boundary to the boundary on a ball, then this immersion will be minimal and free boundary if and only if the coordinate functions are Steklov eigenfunctions with eigenvalue 1. So you have the normal derivative of each coordinate function is itself. Okay? And again, as in the other case, you can forget about the immersion and then look at this eigenvalue problem. You have your setting is you have a compact surface with boundary. You give a metric, you look at the first non-trivial Steklov eigenvalue, and here you just need to multiply by the area of the length of the boundary. The way it's defined the eigenvalues, you have this will make it the scaling won't let you get always infinity. And you ask the same questions that whether this quantity is finite or not. And the answer again is yes. Weinstock was the first one that looked at this for the disk. Then Fraise and Shane considered for any orientable surface, and then Medvedev checked that it also holds for non-orientable ones. Okay, and again, you ask the same questions. Do we have a maximizing? What do we know about it? So Fraise and Shane, they proved that if you do have a maximizing, then your surface endowed with this metric can be immersed in an Euclidean ball as a free boundary minimal surface by first eigenfunctions. And Detrides also worked in this setting, and he proved the existence of a maximizing metric if you concentrate on a conformal class. But here he needed this lower bound for the functional, but it's believed to be true in general, so it's not like a restriction. So if you want to prove that, that'll be awesome.
Is the boundary assumed to be?
It's over there.
Any number of boundary components or?
Any number. Okay, and he also proved this, the equivalent of that, inequality. He also proved that here, if you have sigma, gamma k, genus gamma, and k boundary components, if you do have these two gap inequalities, then you can conclude that the maximizing metric exists for sigma gamma k. Okay? And in the same paper, by Kirkbooking, Kuzer, McGrath, and Stern, they were able to prove a kind of a weaker inequality like this. And from there, using the treatise, they were able to conclude that the maximizing metric always exists for any surface of genus 0 and 1. Okay? Any number of boundary components. Okay. Good. Now, what about the known cases? So here we have, well, the disk was done by Weinstock. We do have the flat metric as the one that maximizes. The cases of the annulus and the Mobius band, they were done by Fraise and Shane. For example, in the annulus here, you have that the metric from the critical catenoid is the one that maximizes, and they actually characterize the critical catenoid as the only free boundary minimal annulus that you can immerse by first eigenfunctions. And they prove the same for Mobius band, putting in B form. Okay, for the case of orientable surfaces of genus 0 in at least 3 boundary components, Fraser and Chain also proved that the maximizing metric exists, and Karpukhin and Stern, they showed that the maximizers, when you pick your surface and you down with the maximizing metric, these surfaces will converge to the sphere, the boundary of the ball. And here is again a picture by Mario where you have your surface with the maximizing metric, and the surface has a large number of boundary components. And yeah, okay, and that's all we know so far. But so we have these two eigenvalue problems. Let me put it here. So we have this connection. So first we have closed minimal. We have M in some sphere, and connected to that we have the Laplacian and the functional that gives you back the functional that maximizing gives you back these kind of surfaces is the one where we take the first normalized Laplacian eigenvalue. Right? And now we have this other connection by Fraser chain, where now we have free boundary minimal surfaces in the ball, the Euclidean ball. And the operator that is associated to it is the Dirichlet alignment. And then the functional that they define is the first Steklov eigenvalue normalized. So yes. Okay. So Wonderstein and I started to think about, what if we do have something similar to this? What if you have a free boundary minimal surface now in a spherical cap? Do we have an eigenvalue problem that gives you back these type of surfaces? So here, Wonderstein and I started to think about free boundary minimal surfaces where you have sigma now in a spherical cap. I will give you a right resization. So we have a spherical cap of radius r contained in some sphere. Okay, so we needed to know whether we do have an operator that is associated to that, and also which type of functional would be interesting, would be meaningful to ask questions about maximizing it. Okay, so the first thing that we need to do was to understand these surfaces. What properties do they have? Okay, so here, that's what we mean by spherical cap. So yeah, it's a geodesic ball centered at the North Pole with geodesic radius r. Okay, so let me put the picture here. I think it would be useful later. So here, this is the x naught, and here are the other ones. And your spherical cap is just here in the top somewhere. Here, and here is the radius r. So this is your spherical cap of radius r, and you know that the boundary here is just the intersection of your sphere with the plane x naught equals. Okay, so the boundary is contained. Okay, so that's the space where we'll be working on compact Riemannian surface with boundary, Riemannian manifold with boundary. All right, so now we consider an immersion here, proper, sending boundary to the boundary, and we do some computations. So if we assume that this immersion is minimal and free boundary, then the coordinate functions will have to satisfy these equations. Okay, so you see that each one of them will satisfy this in your surface, and the normal derivative of each of them is a multiple of itself, but they come with different values. So the first one, phi naught, the first coordinate here, they come with the value negative tangent of r, and all the other coordinates, they come with value cotangent of r. Okay, so that was the first thing that we did. And then we observed that the condition of being minimal, you don't need free boundary, will tell you that 2 is not in the spectrum of the eigenvalue with the Dirichlet boundary condition. So this Dirichlet boundary condition is just, did I put it? Oh yeah, I put it. So it means that if you try to solve this equation here, we only get the trivial solution, okay? When we saw that, we were very happy to realize that this has connections with the Dirichlet to Neumann map with frequency 2, in this case that the 2 appears here. So what is that? So what are these Dirichlet to Neumann with frequency? They are called Steklov problem with frequency. So here you can define in general, you just need to pick a value alpha that is not in the spectrum of the Laplacian with the Dirichlet boundary condition. Okay? So because once you have that, you have a uniqueness in this sense. Given any function in the boundary, you find a unique extension such that it solves this equation in sigma and it satisfies this on the boundary. Okay, so you have this uniqueness. So you can define your Dirichlet to Neumann map with frequency alpha, the alpha that shows up here, exactly as we define here, but instead of picking the harmonic extension, we pick the extension that satisfies this. So you give a function u on the boundary of your surface, the Dirichlet to Neumann map at frequency alpha gives you back the normal derivative of its unique extension, satisfying this, okay? And this operator is also nice. It has discrete spectrum that converges to infinity. They are called Steklov eigenvalues with frequency alpha, but it doesn't have the same property that the first one is always trivial. It might not be trivial, 0, I mean, okay? And of course, when you consider alpha here, the frequency, you put 0, that's your usual Dirichlet Neumann map. So if we go back to the properties that we just proved and we translate into this operator, we are telling that you do have a free boundary minimal surface in a spherical cap if and only if the coordinate functions are the Steklov eigenfunctions with frequency 2, because that's the number that appears here, and it comes with 2 eigenvalues, negative tangent of r for the first and cotangent of r for the other ones. And one thing that you already got for free here is that since we are working with a spherical cap here in the top, for example, we know that phi naught is positive. So it means that it's a first eigenfunction. So in this case here, we already know that sigma naught is always negative tangent of r. So in particular, you see that for the cases that we are interested in, it's not trivial, this sigma naught. And of course, you can conjecture that sigma 1 should be cotangent of r, but still have to prove that, okay? All right. Okay, now, this is, once you define, let me put it here, that I already have the answer. So this is the Dirichlet to Neumann map with frequency 2. And here is the variational characterization of the eigenvalue for this guy over here. So the way we define, that's the variational characterization, the usual one, but we need to check, we need to notice that in the top here, we are taking u hat, okay? And u hat, remember, is the function that is the unique extension satisfying this. Okay. So it means that if you want a test function to estimate sigma naught, you cannot just pick a function that is defined on the whole surface and plug into this quotient, because here it's only for functions satisfying this. So if we work in this generality, every time you want to test function for sigma naught, you first need to check that it satisfies this condition. And it's not very easy to do that. It's quite hard. So to overcome this, because we want to use any test function to estimate sigma naught, we work with metrics that satisfies this condition. The first Steklov, no, not Steklov. The first Laplacian eigenvalue with the Dirichlet boundary condition is strictly bigger than 2. So, because, yeah, so we'll be working with all the functions such that when you look at the first Laplacian eigenvalue with Dirichlet boundary condition, this is bigger than 2. And this is telling me that if there exists a function that is non-trivial satisfying Laplacian u, Laplacian w plus 0 here, and the Dirichlet condition here, these you can solve non-trivially if and only if it's the opposite. Maybe I'm doing the opposite way, but it's something. Yeah, and for the cases that we are interested in, okay, which are these guys, we always have this condition of first eigenvalue being strictly bigger than 2. So for the cases that we are interested, we can do that. So we can you can pick any function that is in W2 and put it here in this quotient. And this is even only if, kind of. So if you take lambda 1 less than 2, then this guy is actually negative infinity, so you don't have the equality. So we do need to work here to have this characterization. Okay? Okay, now that we have the operator, now it comes the functional. How do we define the functional? And it has to be a meaningful function, no? It has to be a functional that it makes sense to maximize, and when you maximize, you get back an example of such surface. So the first thing that you can notice is that in the first two cases, the first eigenvalue was 0. So here lambda naught always 0. Here also sigma naught is always 0, so they don't need to work with them. But in our case, in general, we don't have it, and actually for the case that we want, they are not trivial. So we needed to work with sigma naught, but sigma naught is simple, it's not enough. So we need to work with at least 2 eigenvalues. So it will be a little bit trickier than the first 2. But then, how do we make this functional? Do we sum them? Do we multiply by the area? Do we multiply by the length of the boundary? How do we get it? So the way Brandes and I did was, suppose here that we have sigma, now a complex surface with boundary, gamma the genus, L the number of boundary components. We are going to denote by M of sigma the space where we do have this condition. So the first Laplacian eigenvalue with the Dirichlet condition is strictly bigger than 2. And well, since you have a compact surface with boundary, you know you have a conformal cover of the 2-dimensional spherical cap. Okay, and this cover has degree at most gamma plus L. Okay, the topology here. Okay, it's proper since boundary to the boundary, so the first coordinate is constant cosine of r, and the other two satisfies this. You're in the sphere. And then it comes the trick that in the literature sometimes it's called the Hirsch trick, where you can balance your map so that at least 2 of your coordinate functions you can use as test function for the sigma 1 eigenspace. So you can balance to have u1 and u2 have test function for sigma 1. And that's what we use. So to estimate sigma naught, you pick U naught, you can take any one, you pick U naught. To estimate sigma 1, you pick the other two. So you have that for the variational characterization that we have. And when you add them together, you get this. So you see that on the right-hand side, I only have a quantity that depends on the radius of your geodesic ball and the topology of your surface. And here is just, the properties that we have. So this, when you add this to this, you got here it's constant cosine of r, it comes here. These two you add, you have the sine, and then comes the boundary. This term comes from here because you are in the sphere. And then here, this term, you use that the degree is at most gamma plus L to get this upper bound, okay? So, Vanessa and I defined our functional as the left-hand side here. So you give me, you are working in a spherical cap, you give me a metric, we take this functional over here, okay? So you have a linear combination of the two eigenvalues multiplied by the boundary, and then you plus 2, which is the dimension of the surface, times the area. And by the calculation that we just did, this functional is bounded from above, so it's promising. And you can also prove that it's sharp for the case of the disk, so that's quite nice. And that was our first result. So we defined our functional, we proved that it's uniformly bounded from above, and this upper bound is sharp in the disk. So of course, since it's a uniform bound, we already get for free that this guy is finite. If you take this two over all possible metrics in our space here, and then you can ask the same questions that we had in the other cases. So do we have a maximizing metric? What do we know about it? And in our second result, Vanessa and I, we proved, which is the analog of Nadarashvili and Frazen-Chain in their contexts. So we have, if you do have a maximizing metric for our functional, then the surface endowed with this metric can be immersed in a spherical cap as a free boundary minimal surface by first eigenfunctions. And by first eigenfunctions, we mean the first coordinate is sigma naught eigenfunction, and the others are sigma 1 eigenfunctions. Okay? And if you want to ask the question where you just restrict yourself to a conformal class, you can prove a similar result. If you do have a maximizing the conformal class, you get a similar result, but only a harmonic map, not minimum. Okay? Excellent. And to talk about our third result, I first need to present you with a family of free boundary minimal analyte that exists in spherical caps. So here, Otsuki and Lucarmo and Dachi, they studied the concept of rotational surfaces in spheres, and they kind of characterized them, the ones with CMC, they characterized them and they gave parameterization for them. So for example, this one is the parameterization for minimal rotational analyte. Oh, sorry, not analyte. Rotational minimal surface in the sphere. Okay, and yeah, let me mention that Otsuki, he did the minimal case, and then Lucarmo and Dachi, they did the general CMC case. And this parameterization here is the one that you can find in Lucarmo and Dachi. Otsuki, he had a different point of view, and his parameterization we found harder to deal with. So in our paper, we worked with this parameterization. Okay. And in a paper by Li and Chiong, they observed that in any spherical cap, you can find a parameter, that's the parameter that is here. You can find a parameter and you can cut these rotational surfaces by a value here such that when you look at this restriction, you're going to get a free boundary minimal analyte in the spherical cap. Okay? And a couple of months ago, Manuel Ruivo de Oliveira, he's a student of Ilana Fraser, he posted a paper on arXiv where he gave the whole details of the existence of such minimal analyte. In the paper of Li and Chiang, they only gave a rough sketch. So he gave a very nice full detail for that. Okay, so we do have free boundary minimal analyte here. in our spherical caps. So in our next result, we characterize these rotational minimal annuli as the only ones that can be immersed in a spherical cap by first eigenfunctions, similar to the case of phasing chain for the critical cut point. Okay, so here we prove that if you are with an annulus and you assume that you can put in a metric here that you can immerse in a spherical cap as free boundary and minimal, and you assume it's by first eigenfunction, so you're assuming here that from 1 to n you do have sigma 1 eigenfunctions, then you can prove that the dimension has to be 3, okay? And this metric is the one that comes from the rotational annulus that we just saw. Okay? The first remark here is that we don't need to put that it's sigma, that phi naught is a sigma naught eigenfunction, because we already have that, just because it's free boundary and minimal, so don't need it. And the second thing is, if we combine the two results that we have, if you remember the second one that we had, we proved if we do have the maximizing metric, then the surface can be immersed by first eigenfunctions, that is in general, any topology. But here we proved that if it's an annulus, then, and it's by first eigenfunctions, it has to be the rotational ones. So if you combine them, we are saying that if we do have the existence for the annulus, the metric that maximized should be the one that comes from those rotational examples by Otsuki, Lucarmo, and Dachi. Okay. And you probably are thinking, it makes sense to ask about the existence of the maximizing metric in general. And you might also be thinking whether our condition here of, the first eigenvalue for the Laplacian with the Dirichlet boundary condition might cause an issue that you might get out of your space when you try to maximize. And to give you some motivation that we should be safe, that it does make sense to look for a maximizing metric here, that you can show as a motivational result, you can show that if you do have, like if you have a sequence, if you have a sequence of metrics in our space, so it means that we do know that the first eigenvalue of the Dirichlet boundary condition of these guys are strictly bigger than 2. If this sequence are such that it converges smoothly, just so you have an idea, to a metric G with out of our space. So, for example, if it's the boundary of our space, right? So the Dirichlet boundary condition of this guy, it is 2. Then you can show that actually this implies that when you look at the sigma naught eigenvalue of the sequence, it is converging to negative infinity. So if these guys are going to the boundary of our space, they are not going to the maximizing our power function. Okay, they are not going to be the maximizing. Okay, good. So in the last few minutes, I would like to give an idea of how to prove this last result of the characterization of the analyzed.
It is often the maximization problem.
Oh yeah.
This just gives hope. Gives hope.
Gives hope, yeah. It gives hope. That makes sense.
Okay.
So it makes sense to ask. It's not like our restriction here will, say that. Yeah. It's just a motivation. Like it makes sense to ask. Okay. So before I give the general idea, let me just mention a few words that they also have this connection between minimal surfaces and eigenvalue problems. There are a whole literature of that, so I'm gonna just mention a few. So you can pick. Let me put our functional here, right? Not going to. So for the case of the Laplacian, You can consider the higher order. You just change lambda 1 by lambda k. You can ask the same kind of questions. We have a lot of work. We have Al-Sufi, Elias, Karpukin, Nadrashvili, Penskoy, Peterovich, also Petridis, and many others. You can, of course, do the same here. You pick, instead of sigma 1, you put sigma k, ask similar questions. And we have Fraser and Chain, Jihoa Peterovich, also Petridis. And we already have some results for a higher order for our functional. So Medvedev, he took our functional and he considered the higher order. So he put sigma k here and he proved some results for that. Okay. So we have a bunch of nice papers for this kind of relationship. Okay. So let me give this sketch. Yeah.
How is links with the free boundary problem? When you maximize the level K,
Yeah.
how that problem relates to the free boundary?
It is, you're going to get the same, for example. Yeah.
But you have more components?
No, it's just that instead of having eigenfunctions for this guy, you are going to get eigenfunctions for sigma k. So you get the same result, but the first coordinate will be sigma naught eigenvalue, and the other one will be sigma k. And I think it should be the same.
Okay.
Yeah. So to prove our theorem of the characterization of the case of the analyst, one of the ingredients that we need is a Courant nodal domain type result in our context. And this was done by Asma Hassanejad and David Scher. So they proved that in general here, if your metric G is exactly in our space, first Dirichlet, not Dirichlet, the first Laplacian eigenvalue with the Dirichlet boundary condition is strictly bigger than 2, they proved that when you look at the number of nodal domains of the eigenfunction sigma j, this is just at most its order plus 1. Okay? And once we have this Courant nodal domain type result, Vanderswijn and I were able to show that you can get an upper bound for the multiplicities of the spectral eigenvalues with Dirichlet, with frequency alpha, or 2 as we are interested in. We proved for alpha in general. So we have that the multiplicity of sigma j is 4 times its genus plus twice its order plus 1 at most. Okay, so for example, if you're working with an analyst, then, because it's the case that we are interested in, right? So if you're working with an analyst, then when you look at sigma 1, then this will be at most, gamma will be 0, so it will be at most 3. Okay, so we have an upper bound for sigma 1. Okay. Good. Now I'm able to show at least a particular case of the proof of this result. So here we have an analyst, and we are assuming that it's going to a spherical cap as free boundary minimal surface by first eigenfunctions. Right? So the first thing that we notice is that by this upper bound on sigma 1, we already conclude the dimension. You have an emergent, so we do have that any must be 3. And now our job is to show that using that the coordinate functions give you that sigma naught is negative tangent of R and sigma 1 is cotangent, exactly cotangent of R, then we need to show that our surface is rotational. So how we do that? Well, we have analyst, so it is conformal to the cylindrical metric, right? And me here, it's a positive function. So to prove that sigma is rotational, the first thing that you need to prove is that the metric is rotational. So we need to prove that this function here does not depend on theta. Okay? Well, you know the relationship between the Laplacians and the conormal for each metric, and then you do some, go to the other coordinate, differentiate, go back, and you get this equation here. So you see that in the middle, it's exactly the term that we're going to prove that it's 0. So it's basically you want to prove that not only the coordinates of phi are like eigenfunctions, we'd like to prove that the derivative with respect to theta are also eigenfunctions somehow. So I will show you the case when we have this extra condition. So we assume that the integral over the boundary of this guy here is 0, and this makes things much simpler because with this condition, I'm telling you that I can use the coordinate functions, at least from 1 through 3, as a test function for sigma 1, because my first eigenspace phi naught, it is constant on the boundary, the first eigenfunction, yeah. Okay, and here, well, we have to do some computations. Here is basically doing the second variation of energy to this, applied to this vector field here. So we do some computations. I'm hiding them here, of course. And then this derivative here, we do the same trick. And here where it shows up that we are using, that they are sigma 1 eigenfunctions. Okay, so they show up here. And then we rewrite this equality to resemble the variation characterization of the eigenvalues. Okay, so we have this. And first thing is this guy here is 0. The phi naught is constant. And the fact that 2 is not a Laplacian eigenvalue with the Dirichlet boundary condition tells that this guy is non-negative. Actually, anytime that you have a function that vanishes on the boundary, because of this, you can show that this type of expression has a sign, it's non-negative. Okay? So this last term has a sign, and then this is the part where we use that our the coordinate functions of this guy can be used as test functions for sigma 1. So we do have a sign also for the others. So everybody's non-negative, it's given you 0, every term should be 0. So you get that in fact they satisfy this condition here. So, but this is exactly what we had in the first place. So we are telling that the term in the middle is 0. But then you use that you are by immersion into the sphere, so you can conclude that this guy is 0. So your metric is rotational. And then comes linear algebra classical argument to show that once your metric is rotational, you do get that your surface is rotational. So you can conclude that your annulus should be the one that comes from Otsuki, Dutch, and Dukram. Dukram, Dutch, Otsuki. Okay. And yeah, and this is for the case where we already have that beautiful condition that we already have the test functions. That's awesome. If you don't have that condition, it means that you have to look for test functions. And here we follow the ideas of crazy chain. We look for other conformal vector fields where we can try to get their coordinate functions to work as test functions. But I'm not going to show that here. So I'm going to stop here. Thank you for your attention.
Very much. Interesting and clear talk. Other questions? Yes.
So you got beautiful results generalizing the billion balls will fall in space at constant curvature. What about if you take a ball in the hyperbolic space?
Yeah.
So there, I mean, you could think of it as sitting in the hyperboloid and Minkowski space, and you can have an analogous thing about eigenvalues of eigenfunctions of constant curvature.
Yeah. Medvedev, he considered our functional, the analog of our functional in the hyperbolic case, which is basically the same, but instead of having cosine, where's my sign? My sign is over here. I hope Madison is not seeing them. So you put the hyperbolic cosine and the hyperbolic sine, and you do need a minus sign just to make things correct. And he considered this functional, but this functional in the hyperbolic space, it's not bounded from above, so you cannot ask maximizing questions, but it is bounded from below, so you can ask minimizing questions.
Because of the minus sign.
Yeah, it complicates the minus sign. I don't remember it's here. I think it's here. And it complicates it, and yeah. So Medvedev,
Right, for a small ball, pretty well behaved, and maybe long states. Because it's sort of a perturbation of the Euclidean case.
yeah, maybe yes. Yes, then. Say it again.
Are there any homogeneous examples of three paths?
Yeah. No, we need that. Yeah. So we do need Karpukhin, McGrath, Kushner, and Stern kind of result to get them. Yeah. I don't know. Yeah, would be awesome. Yes. Wow.
So in these results about surfaces without boundary, you get that you get, according to the result, but there's a would be that you get a minimal inversion in a sphere of some dimension, but the dimension depends on the multiplicity of the smallest eigenvalue. Is there any effective estimate on how that depends on the piece?
Ooh. Well, you do have the upper bound for each multiplicity that depends on the genus, right? So for example, we show here 4 gamma plus j plus 1. So we do have an upper bound, but it's far from being optimal. And it happens the same in the other cases, but I don't think there is a like sharp kind of test that relates the two. Yeah. Would be nice.
Any idea of how about changing the spherical cap by components into spherical caps on a region?
What is the waste?
Well,
You mean the waste or?
take 2 spherical caps with the same center and then take the components. And
Oh.
then you have a region with rotational symmetry.
Uh-huh.
Right?
Uh-huh.
You think about the
You want the
free
intersection?
boundary in there, inside. Because you have a ceiling structure.
Yeah. Wow, it's a question. It's a good question. It might work in the same way, but I don't know. Yeah. It's good.
Examples are all embedded in the part inside the box.
Good question. I should know that. I don't know what if they are embedded, if they're immersed. Might be just immersed.
You have one example for any value, you have an example, right?
That's a good question. We do have at least one, but we don't have the uniqueness yet. Not yet. Like Vandus and I, before trying to prove the case of the anodes, we did check whether we had the existence, and we kind of plot the relationship between the parameters, and we saw that it's not clear that it's going to be just one, but would be, I hope it's just one to be beautiful as the loss. Yeah, but it's not clear yet.
Let's thank Anna.
El caso muy bonita, Sara, muy bonita.
Gracias.
El caso del disco se hace también con un tipo.
Say it again, the case of
Oh, in the disc case, not analysis.
yes.
You also can apply a home argument there, so you have a. How do Nietzsche proves that we have bring the ball
Yeah, and then here we do have it should be the B2
It's again the same argument, it's of differential.
Siempre que tenga Porque igual existe una línea de profesora. Que nunca se no sé pronunciar.
¿Cómo? Mas-
Joaquín está. Yo me lo sé porque como es Joaquín,
Claro, pero bueno, pero es que esto no es yo. Cuando tienes dos superficies que se cortan en ángulo constante,
Ajá.
y en una de las superficies, el nivel de está grabado.
Carmo.
muy
Y le
bien.
mando la foto a Agus.
Ah, sí. With the sign. So you
Con el
see?
signo incorrecto, porque te lo he hecho antes de que lo corriera.
Oh, damn.
Hay muchas cosas que me no, pero
Grazie, grazie.
por dar
Ma per me è la prima volta. Questo è.
Either for but it's based on, I mean, it's based on
Hi, can you say anything about the nodal geometry in this case? Like number of nodal domains in this office, something? Yes, it's I think it's the work by Asma and David. So they proved that at least for the metrics that we are working with, we're the first of this they do have an upper bound. The number of nodal domains is at most the order of your eigenfunction plus yeah, they do have that. Yeah.
In your case, was it D2?
In what? B2? What is yeah, exactly. Because it's I don't think I wrote it down, but it's the eigenfunction. It's the eigenvalues for D2. And they proved for D alpha, where alpha is not the spectrum. Are you studying here? Yeah. Nice to meet you. Nice to meet you.
When I saw that there was
You finish, right? Yeah, you can. So, but sometimes the best model to work with these surfaces, it's not the compatible, it's the how it's called. It's just much easier because you have a nicer parameterization. The equations become more feasible, but you can ask the same type of questions. But if you want to have a free boundary at infinity, that's what you're asking. Let's see if I remember any result. Just you have to make meaning of what you mean by being orthogonal to infinity. Because then you are telling that you'd have to be vertical, right? To have yeah, you have to make sense of what you mean. But I don't really know you just need to make sure that your problem makes sense, that you have a few examples, make up the theory. Yeah, so you have to understand first what you mean by a free boundary. control.
You want
Yeah, that's, oh, take the limit. Yeah, that's one thing. Then you can read the paper by method that because you already takes the balls on the eigenvalues. So you can see what happens.
And also, now you can string only maximizes, right? Can
Yes.
you suggest critical points of this?
Oh yeah, of course you can. You have to. You can, if you even prove something like if it's bounded from below, you can ask about minimizer. Yeah. That'll be nice questions.
Yes, when you said about when we take cos hyperbolic, we can said it is bounded to.
It's bounded from below, but not from above.
So we can talk about
Minimizing the functional, but not maximizing. Yeah, thank you. Big fan. Oh sì, tu vas parler de quoi?
Justement, le résultat de l'existence
De
de la topologie existante. Les quatre auteurs disent deux parmi deux d'affilée, il y en a un qui a topologie. Et du coup, je vais pouvoir présenter ça. On a payé.
Tudo bem, então,
Já posso falar português,
nativo.
Só para contar que acho que ainda não li esse artigo de Mundo do Oliveira, mas acho que nessa parte da assistência da superfície.
Ele próprio estudante?
Não provo, mas ou seja, acho que nós temos também um resultado parecido, porque nós provamos uns meses atrás a existência de anéis mínimos não rotacionais.
Sim.
Inverso.
Sim.
E para provar isso também provamos a existência de modelos mais gerais de.
Mas era mínimo na esfera, né?
Mínimo na esfera,
Sim.
na esfera da
esfera.
Sim, da esfera.
Mas ela tá esférica.
Sim. E provamos para a mínima, por outra linha constante e também no caso hiperbólico. E dava dois exemplos embedidos, mergulhados.
Ele consegue. Não rotation.
Nós provamos no rotation, mas para provar isso, o que